Alrighty nerds, we back at it. We're going to go ahead and tackle the end of lesson 1.1, 1.2 from Algebra 2 Honors. And yesterday we finished up finding domains of functions algebraically. Today we're going to move on to some more things that can be done with functions, more properties of functions. We'll start by talking about inverses. An inverse relation is a rule, an equation, fingers crossed a function, you never know, that maps the range of a function back to its domain. What does that mean? Let me make up some numbers. What that means is if I have an equation, I have an f of x, a function in terms of x, and I plug in a number for x like, I don't know, 2. The equation does some math and a y value comes out. Let's just say it's a 5. What the inverse relation would do is it would take that 5 and it would do some math and it would hand you back the 2 that you started with. So the inverse's job is to undo all the math that a function does. That means that the entire domain of a function becomes a range. An inverse's job is to take that range values and turn them back to the domain values. Graphically, an inverse is a reflection over the line y equals x. And like I just said, it switches basically domain and range. So all of your x's from the original function are now y's. Hold on, I'm saying this wrong. No, I'm saying it right. If it was all of the x's on the original function, they're y's on the inverse. If there were y's on the original function, they're x's on the inverse. Yes, sir?
You have another packet.
I do. Over there in the absent bin. Don't make him cripple over there. Someone get him a packet. Look at his broke leg. Or ankle or something. What's broken? All of YouTube wants to know.
I tore my MPFL off the bone.
He tore something off his bones.
Yep.
Awesome. That sounds fantastic. Where's he going? Should be the bottom left-hand tray. No, I don't have any more. Anyway, what I was saying? Oh, so domain and range have switched places. The domain of your function is the range of its inverse. The range of your function is the domain of its inverse. This makes a graph rotate 90 degrees. It makes it turn sideways. But I put it in quotes like that because we try not to rotate things in algebra because rotations create non-functions sometimes. However, if the inverse of a relation is a function, we call it the inverse function instead of saying inverse relation. Inverse function is denoted like this. And we read that as f inverse of x. That's not an exponent. I know it kind of looks like it. It's not. And if you say f to the negative 1, I'm going to correct you. I'm going to say, oh, you mean f inverse. F inverse of x. In mathematics, it's kind of a special deal if a function has an inverse that's also a function. When that happens, we say that our original function is 1 to 1. Literally, for every x, there is one y. For every y, there is one x. 1 to 1. So if we take you back to the abstract relations that we had here, this one was a function because for every x, it has one y. But right there, for this y, there is not a single x. There's 2 x's. So even though this is a function, it is not a one-to-one function. Because it didn't satisfy for every y, there is one x. So what that tells us is, if I could get an inverse relation for this function, the inverse would not be a function. It would break that rule. Now, if we have a graph of a function, we can tell if it's 1 to 1, meaning its inverse is a function, if it passes the horizontal line test. And the reason why is because to find an inverse, I told you it basically rotates 90 degrees. So something is a function if and only if it passes the vertical line test straight up and down. Now, if our graph passes the horizontal line test, finding the inverse would have the result of rotating at 90 degrees, which would then be a vertical line test on the inverse. So if our original can pass the vertical line test, making it a function, and pass the horizontal line test, then we know it's one-to-one because that means its inverse is also a function. So we have to be able to pass both tests to be one-to-one. And that'll be easier to understand when we come down here to these examples. But beforehand, we've got a couple examples about the inverse only. This skill is not in your textbook from what I could find, at least not this early, which means it will not be in the homework, but I find it informational and important. So I figured why not do it now? We're going to sketch the inverse of some crazy thing that I created. We got a straight line, a quarter of a circle, and another straight line, but these two straight lines don't have the same slope. Well, I told you that in order to get an inverse, all your x's and y's switch places, right? Because it's the reflection of the line y equals x. What I'm going to do is I'm going to grab 4 specific points. This one, that endpoint, and this one right here because it lands in a nice pretty spot. I didn't feel like going to this one because I would have to estimate. Those 4 points, I'm going to write them out as xy's. Got -4, -4, -2, comma 0. Up here at 0, comma 2. And lastly, this pretty point I chose happens to also be same x and y, 4, 4. What we're going to do is we're going to come along and reflect it over the line y equals x. And when we do that, what we're going to do is just switch the x and the y coordinates for each one of those points. Well, -4, -4, nothing changes when you switch x and y. This one will turn to 0, -2 when we go through the inverse. This one will turn to 2, 0 when we go through the inverse. And just like -4, -4, switching the x and y here does nothing. So I'm going to plot these inverted points, if you will, if you want to call them that. Got one right here again. Then 0, -2 is here. 2 zeros there, and 4, 4 is back up here. This first straight line is inverted to this straight line. From here to here is the inversion of this quarter circle, so I have another quarter circle. And then this line segment here to here is inverted through this line segment here to there. Now, check this out. I'm going to put the line y equals x on there. And I hope that it's pretty clear that my inverse is literally a reflection across the line y equals x, simply by switching x and y. Not too bad, right? Isn't that neat? All right. This used to be a question that I would put on my Algebra 2 tests back when I taught regular Algebra 2. What I consider to be free points as long as you understood the mathematics. It says, hey, I'm telling you that the point 2 comma -3 is on a function's graph. So what's a point that's guaranteed to be on the graph of the inverse? Who can help me with that one? I'm still trying to learn names. Ilya? -3 comma 2, way too easy, right? Literally, switch x and y. You know I'd have people miss that every single year? No joke. Yeah, you just switch x and y. Done. Guaranteed it's on the inverse's graph. Ta-da! All right, back to skills that are definitely in the book and in your homework. And that's looking at graphs and seeing if they are one-to-one. Once again, one-to-one means it is a function, so it passes the vertical line test. And its inverse is a function, which means it has to pass the horizontal line test. So in order to be one-to-one, it has to pass both the vertical and horizontal line tests. So I'll be looking for 30 voices today, minus the couple people that are absent. Looking for a yes or no. Class, is this one-to-one? No, of course not. And the reason why it is not one-to-one is because it's not even a function. It fails the vertical line test. In lots of places, I'll draw one of them. There we go. X equals 3 has more than one y value associated with it. Fails the vertical line test, is not a function, therefore is not one-to-one. Again, like 28 voices, is this graph one-to-one? No, it is not. Now this one is a function. It passes the vertical line test, but it fails the horizontal line test. Watch, if you turn it sideways, that's clearly not a function. It will fail a vertical line test, but any vertical line on this sideways graph was actually a horizontal line on the original f of x. So it's a little more clear about what I was talking about when I was showing you the pencil, like it rotating, and now the horizontal line becomes a vertical line. Okay. And then this last one. I am going to go ahead and tell you that x equals 0 is a vertical asymptote, so the graph will never touch the y-axis. And I'll tell you that y equals 0 is a horizontal asymptote. This one will never touch the x-axis. So class, is this graph one-to-one? Yes. Yes, it is. It passes the vertical line test and the horizontal line test. And you know what's really cool about this graph, actually? This is a very special function. This is the graph of 1 over x, y equals 1 over x. Its inverse function is 1 over x also. It's its own inverse. We call it self-invertible, which is really cool. You don't have to know that yet. But if you were to sketch the line y equals x, I hope it's obvious that the curve is identical on both sides of that green line. So reflecting it over the green line I just did would do this. You'd get the exact same graph, which is pretty cool. At least I think it is. I'm a big old nerd. Everybody comfortable with the idea of one-to-one? Okay. This whole page is nothing but knowledge. The whole page is devoted to symmetry. There are two types of symmetry that we will discuss in graphs. Those two types are line symmetry and point symmetry. A graph has line symmetry if it can be reflected over a vertical line so that each half of the graph maps exactly to the other half. Okay, what? This parabola, this line, called the line of symmetry or axis of symmetry, perfectly cuts that graph in half so that its left side is identical to its right side. Every parabola has line symmetry. In fact, that's one of the ways that we graph them. We say find the vertex, get the axis of symmetry, find one more point, and then reflect it over and connect the dots, and you're done. Every parabola has line symmetry because it can be folded in half perfectly on a vertical line. Cool? Okay. The other kind of symmetry that we discuss is point symmetry. A graph has point symmetry if spinning it a half a circle changes nothing. So if we say maps it onto itself. But if you can turn it a half a circle and you get back the same thing you started with, that graph has point symmetry. So I'm going to do my best to draw a circle so that both of those points are on its diameter. Just trying to show you that if I turn it a half a circle, this point this whole side of the graph becomes this whole side of the graph, but then this side of the graph becomes this side of the graph. So spinning it half a circle changes nothing. And this one happens to be special. We would say the point of symmetry here is actually an inflection point. You don't have to know that vocabulary this year. You'll know it'll be more important next year. But for right now, I just figured I'd tell you. So then if those are the only two types of symmetry that we talk about, what's going on in the bottom box? The bottom box are special cases of line and point symmetry. They're special cases. If a function with line symmetry has its line of symmetry on the y-axis, then we say that is an even function. So if you have a line of symmetry on the y-axis, you're dealing with an even function. That's if you have the graph to look at. But what if you don't? What if all you have is the equation? Well, we're not going to spend our time graphing everything just to see if it's even or not. Instead, what you do is you realize that if you're symmetric over the y-axis, that means when you have a positive x value, it's going to give you a y. And if you use its corresponding negative version, it gives you back the exact same y. Because those two x's have the same y. So algebraically, what we do is we replace all of our x's with negative x's. And if replacing your x's with negative x's looks like it did absolutely nothing, then you're dealing with an even function. All right? This one here that they're showing you is y equals x squared. A special case of point symmetry are functions with odd symmetry. Functions have odd symmetry if the point they're symmetric around is 0, 0. So if your point symmetry happens to be centered around 0, 0, we say that function has odd symmetry. Here, on this side of the graph, my x's and my y's are both positive. Here's the exact same shape, except for the fact that it's upside down and backwards, meaning both the x and the y are negative. From here, my x went from positive to negative, and my y went from positive to negative. Algebraically, substituting in a negative x gives you back a negative y. Which means if you replace all of your x's with negative x's, the result is it just looks like you multiplied your whole function by negative 1. I want you thinking of it as negative 1 times f of x. If it looks like all you did was multiply your entire equation by negative 1, you have an odd function. Okay? So, once again, oh, and by the way, this example that they gave us actually is an odd function, but we could have had this shape anywhere on the xy axis, or xy plane, excuse me, and we still would have point symmetry. But putting it at the origin is what made it an odd function. Easy enough? Okay. So like I said, we're not going to be identifying even and odd functions using graphs. We'll be identifying even and odd functions using algebra. But one last time, both tests require you to replace your x's with negative x's. So the first thing we will do is replace our x's with negative x's. We'll follow the order of operations, and we'll see what we end up with. In part A. We're going to replace our x's with negative x's, and here's how we're going to do that. Everywhere there was an x, I would like for you to open a set of parentheses and leave it open for a moment. I'm asking you to do it this way because I'm preparing you for transformations. And you have to do this a lot with transformations, and it's better that you get used to it now. Everywhere I had an x, I'm going to throw a negative x. And now I'm just going to follow the order of operations. I'm going to do what math tells me to do. Here this says negative x quantity squared. That means negative x times negative x. When I multiply two negatives, what kind of number do I get, class? Positive. And anything times itself is squared, right? So negative x times negative x is positive x squared. Oh, and here's minus 3. Oh, but x squared minus 3, that's my f of x. So replacing my x's with negative x's resulted in no change at all. And because there was no change, we could say that is an even function. It was at this point in first period today that someone said, well, could we have a different example, maybe one that was just a little bit more intricate so we could see what we're dealing with? And I said, absolutely. So I made this up. It's an extra example. We're going to check for even and odd. Oh, by the way, if a function is neither even nor odd, you just say, that says neither for some reason. That's supposed to say neither. It's the first time that I've seen that. There we go. Even odder. Neither. Any Minecraft fans in the room other than me? Ryan doesn't want to say him, but I know he plays Minecraft. Yeah, you do. Yeah. Brody. I don't want to be dealing with the nether. I'm not trying to deal with any sky squids today. Okay. F of x. Let's do this. Making this one up. Let's check it for symmetry. Is it even or is it odd or is it neither of those? Let's find out. First thing we do is replace every x with a set of parentheses.